del cross A curl of vector field A. If you operate the del operator with a scalar quantity, you will get the vector quantity. This is called the gradient of scalar field. Gradient of scalar field. So this is all about the del operators. Then I will discuss a problem based on what we have learned till date. The question is, a point is given, a point and a vector is given, and we are trying to express that point and vector in different coordinate system. Given a point, given points, point P minus 2, 6, 3, this is given point, and given vector is, vector A is equal to yax plus x plus z ay. We have to express this vector, we have to express point P and vector A in, since this vector and point are represented in Cartesian coordinate systems, we have to express this point P and vector A in cylindrical coordinate system, cylindrical coordinate systems and spherical coordinate system. We have to express this point in cylindrical coordinate systems and spherical coordinate system. After that, you have to find, or you have to evaluate vector A at point P, in the Cartesian cylindrical and spherical coordinate system. The question is very simple. We have a point P and a vector A. We have a point P and vector A, and we are trying to express this point and vector A in cylindrical coordinate system as well as in spherical coordinate system. After expressing, you have to evaluate the value of vector A at point P in Cartesian system, cylindrical system and spherical system. So solution for this is, at point P, the x value is minus 2, y value is 6 and z is equal to 3. We have to express this point in cylindrical coordinate systems. First I will transform this point in cylindrical coordinate. In cylindrical coordinates, we have to express this point in terms of rho, phi and z. So z value remains constant. We have to calculate the rho, radius of cylinder and azimuthal angle, and with the help of the equations which I have derived, we can calculate rho, radius of cylinder, by using this mathematical equations. under root x square plus y square. So minus 2 whole square plus 6 square under root, this is equal to under root 40. So the radius of this cylinder is under root 40. After this, we have to find the azimuthal angle phi, and phi is equal to tan inverse phi by x. Tan inverse phi by x, this is equal to tan inverse 6 by minus 2, tan inverse minus 3. If you calculate this value, then the phi value is equal to 108.43 degree. So what we have done, we have expressed this point P, which is given in Cartesian coordinate systems, to cylindrical coordinate system. We have converted that, or we have expressed that point P in cylindrical coordinate systems. Then our next target is, we are trying to transform the point P in spherical coordinate system. In a spherical coordinate system. In a spherical coordinate system, we have variables r, theta and phi. So again, we have to use the relations which we have discussed earlier in spherical coordinate system and the Cartesian coordinate systems. So r is equal to x square plus y square plus z square under root, this is r, and this is equal to minus 2 square plus 6 square plus 3 square. If you simplify this, then you will get under root 49, and this is equal to 7. So the radius of a sphere you have calculated is 7. After that, you have to find the value of theta, and theta is calculated with the help of this equation, is equal to tan inverse x square plus y square under root divided by z. You have already calculated this term, under root x square plus y square. So this is equal to under root 40 by 3. So the theta is equal to 64.62 degree. After this, you have to calculate the phi. Phi is same as this which we have calculated in case of cylindrical coordinate system. Phi is equal to tan inverse y by x, and this is equal to 108.43 degree. So what we have done till now, we have expressed point P, which is given in Cartesian coordinate systems, to cylindrical coordinate system, and the radius of cylinder is 40 under root 40 comma 108.43 degree. Then the z value is 3. We have already converted this point P in spherical coordinate systems. P is equal to 7 and theta is equal to 64.2 degree and phi is equal to 108.43 degree. So we have converted the point P in cylindrical coordinate system as well as in spherical coordinate system. So the next target is we have to calculate vector A at point P. So in the Cartesian system, vector A at point P is given as vector A is equal to yax plus x plus z ay, unit vector ay. So we have to calculate vector A at point P in Cartesian system. The value of x, y, z at point P is given. We have to substitute this value in this vector. So y 6ay, 6ax, ax plus minus 2 plus 3 ay. So this is the vector A which you have calculated at point P. If you consider vector A and the component of this vector, x component of this vector is y component of this vector is x plus z, and z component of this vector is 0. So we have to transform this vector in cylindrical coordinate system as well as in spherical coordinate systems. So the next target is we are trying to express vector A in cylindrical coordinate system. So we are trying to find the value of A rho, A, phi and Az component of vector. Using the matrix, we can do that. Here the cos phi, sin phi, 0. Differentiate this with respect to phi. You will get sin phi, cos phi, 0, and this is 0, 0, 1. Here we have to write ax component, then ay component of vector A and az component of vector A. Using this matrix, we can convert a vector which is given in Cartesian coordinate systems into cylindrical coordinate systems. So from this, if you write a rho component of this vector, so a rho component of this vector is simply y cos phi plus x plus z sin phi. So simply multiply this, and a phi component is minus y sin phi plus x plus z cos phi, and az component is 0. Here we have converted, but in this conversions you can see that we have y which is in Cartesian coordinate systems. Also we have x and z term, a variable x and z which is used in Cartesian coordinate systems. So we have to express this x, y, z in